pleasure to introduce Fulton, who is the Degeneracy Distinguished Professor of Michigan. I'm supposed to say a few more words. So, many of us probably have seen his many books, and so Phil has been awarded the Steele Prize for exposition specifically for his book on intersection theory and many other books. Well, he's also well known as a cultivator of young mathematical talent, and according to the official records of the math genealogy, he has 24 students. I'm very fortunate to be among that. And if you count the descendants, again, according to the official record, there's 126. And there's at least one more of us in the audience here. So, and then if you count postdocs and other people that use yourself in any other way, then at least a order of time. Without further ado,
thanks very much. It's a pleasure to be here. Well, I'm going to try to tell a 170-year story, and that's a bit of a challenge. I could stand up here and just write down names and dates, and I would use up the hour. So it's going to be a very selective history, just a few high points, and I'll try not to write very many formulas. And probably the theorems won't have as many hypotheses as they should. But it's quite a wonderful story. So and it starts in a remarkable period in the middle of the 19th century. Before then, algebraic geometry, I mean, Newton had looked at plane curves, and people had looked at their singularities, and there were Fluker equations for curves and the dual curves. And then there was Abel's wonderful work about analysis on Riemann surfaces. And Bezout had said predicted how many solutions a bunch of equations should have. But, and they knew what projective space was, and parallel lines, and making them intersect at infinity, and duality between points and hyperplanes, and this kind of thing. But it was a pretty primitive subject of it. And then all of a sudden, in these 2 or 3 years, I mean, a bunch of fantastic things happened. So this is not quite in order, but one of the first things is that Cayley and Salman discovered that a smooth cubic surface has exactly 27 lines on it. And my colleague Igor Dobychev said that's when algebraic geometry started. I mean, and it was a tremendous discovery. It just leaps and bounds beyond anything that had been done before. And in that period, Steiner asked this question of how many plane conics are tangent to 5 given plane conics. And he gave the number of 7,176, which is wrong. And the reason it's wrong is because his intersection theory wasn't very sophisticated. The excess intersection problem, which we'll talk about. But again, that started the whole field of enumerative geometry, which continues today, and mirror symmetry, and all of this fantastic stuff going on. And a third one that I want to say just a word about is Salman, who plays a role in a lot of these stories. He is actually studying the duals of surfaces to generalize the duals of plane curves that they know about. So looking at hyperplanes tangent to surfaces. He ran into this problem. You had 3 surfaces in free space, and you wanted to know the intersection of them, but you knew that it contained a curve. So it should be a finite number of points, and it contained a curve together with a finite collection of points. So you can imagine this, the three surfaces all containing some fixed curve. And then the question is, how many points are there? So without the curve, if they were all points, is what Bezout would predict. Bezout would say the number of points would be the product of the degrees of these 3 surfaces. But if you've got a curve sitting there, that's not the right number. And what is the right number? What do you need to know about the curve to figure out how many points are there? And this is the first instance I know of what we call excess intersection theory. You're trying to intersect things that they should intersect in codimension 3, but there's something codimension 2. And how do you deal with this? And McPherson and I worked hard to study that in the 1970s. But in fact, Salman in this period wrote that down and solved it. I don't know his numbers are correct, but It's quite amazing that he could do such a thing. Go home and try it just by hand. Right? Imagine you're in 1847. Okay, so that's not the three things I'm going to talk about. I want to talk about a fourth thing that also happens exactly at this time. And it's a combination of work of Cayley and Salman again, who were involved in two of those three things. And it's this first case of the degeneracy loci. So what's a degeneracy locus? You have a matrix, so an m by n matrix, and we'll talk about the entries can be various things, but for now, take them to be coordinate functions. So on projective space, so that's the completion of affine space, so Cn plus 1 minus the origin with C star action. But take it where n, so these are the coordinate functions, that means it should be m times n, but when you divide out, you have minus 1. So in this locus, you have a locus where, in this vector space, you have a locus. So I'm going to use generally a capital omega for anything that's a degeneracy locus. And this is it's described by saying that the rank of A is less than or equal, well, less than m and n, right? So it's matrices of less than maximal rank. So how do you do that? You take all the maximal minors of this matrix and you set them all equal to 0. Right? And you want to look at that locus. And so let's say it, so let's assume for simplicity it doesn't matter, but that m is at least n. And so we're looking where the rank is at most n minus 1. And in fact, what's true here is that the codimension of this locus is, in fact, it's m, not quite obvious, but you play with it for a while and you'll realize that that's what this locus should be. Of course, if m is equal to n, it's just defined by the whole determinant. It's a hypersurface. So the problem is when it's bigger than n. And that's what the codimension is. But it's defined by all the minors, and so m is the bigger one. It's defined by m choose n minors. So, and generally, this is a much bigger number than this one. And the bigger m is than n, the bigger this number is than this one. So we have a locus that's, you'd like it to be defined by this many equations, and then the zoo would kind of tell you about it. Like its degree would be the product of that. You want to know what's the degree. So if you remember that for if it's something of dimension 0, which I guess rarely would be, it would just be the number of points. In general, if this has a dimension, well, you take something of a linear space of complementary dimension and intersect with it and see how many things you get. So like this is 2 because you intersect with a linear thing and you get 2 points. So that's the problem. That's a pretty elementary problem. Again, go home and try it. Do it by hand. You need some cleverness for this. So it's the difference between these two numbers which make it such a challenging problem. The things they had before 1847 just didn't touch it. Okay, and so let's look at an example of this. Let's take n equal 4 and n equal 2. So we have these, and we're looking where the rank is 1. And let me use a notation. So the Dij is the 2 by 2 minor using row I and row j. So we've got 6 minors that are defining this thing, right? But it's only codimension. It's what's supposed to be 4 minus 2 plus 1, 3. Right? So it's too big. Right? So what do? There's an obvious thing to do. You look at the zeros of some of these minors. So take this minor, right, and take D13 and D14. Right? So this minor, this minor, and this minor. So these are all going to be quadratic equations, right? So if these are the coordinate functions, the Aij's, those will be, we're looking at 3 hypersurfaces of degree 2. And so it's almost this, oh, right? So why isn't it? So if these things vanish, so that's what we're saying here, that means these these two rows are proportional, and these two rows are proportional, and these two rows are proportional. So surely all the rows are proportional, except one. If this row is 0, you don't know anything about the other rows. Right? So in fact, this is it's that union B of A11, A12. The zeros of that. So if those are 0, then all these things certainly vanish. And if these don't vanish, you're in the subject one. Right? And you see, we're exactly in the same situation that Salman was in before. We have 3 hypersurfaces, right, which you'd like to say they intersect in something codimension 3, which is, this is codimension 3. But there's this excess piece that's too big. So what we want to know is what's the degree of this thing, right? So these each have degree 2. So Bazoo would say 2 times 2 times 2 is 8, but 8 is not the answer for this. It's the answer for the whole thing, which is mixed up. So in fact, the degree of this is 4, but that's not so obvious. So already, so in what we call excess intersection, they didn't call it anything, but. And but they gave a general answer. In fact, right. So I'll give the more general setting is, so more generally assume Aij doesn't have to be a coordinate function. It can be any homogeneous polynomial. So, but there is one thing you have to be careful. If you want this to make sense on projective space, any equation we write down has to be a homogeneous equation because it has to be compatible with the action of the C star. Right? So if I take any old degrees of the IJs and I start writing down minors, they're not going to be homogeneous. Right? So I have to be careful. And if you think about it a little bit, the degree of this should depend on the degree of I and the degree of J additively. And for later purposes, I'm going to use X's and Y's for the degrees. Right? So I'm assuming there's some X1 up to Xn and Y1 up to Yn, such that the degree of Aij is Xi plus Yj. Then all the minors are homogeneous. So it's implied. And here's what Cayley and Salman said, and after a few papers, is you write down this expression. So you define C's by this formula, product of 1 plus xi t, so big T. And so I equal 1 to m, and divide by the product of j equal 1 to n of 1 minus yj. So what I take this thing and expand this formally, so 1 plus yj t plus so on, multiply it all out, and define ci to be the coefficient of, if it's used in a k. Define ck to be the coefficient of t to the k in this power series. And then the answer is that the degree of omega is exactly cm minus n plus 1. It's like beautiful, simple, nice, but more to do. But how would you find it and how would you prove it? So this was the first paper before 1850, and there are a whole bunch of people that worked on this between 1850 and 1900. Lots of them are people you've probably heard of if you know some algebraic geometry, some algebraists. And then about 50 years later, the Giambelli, so 1903, 5, 7, he wrote several papers about this sort of thing. And he asked for the general case where you take omega r and fitting in Pn, where you say that the rank of A is less than or equal to R. So not just where the rank drops, but the rank dropped by any amount. And in fact, what it's not very hard to prove. It's not obvious, but the codimension is exactly m minus r times n minus r. But it's defined by a huge number of equations. That's m choose r plus 1 times n choose r plus 1 for all the r plus 1 minors. And the final answer, that, so this is 50 years of work, is that the degree of this thing is given by a determinant whose entries are these C's. And it's an amazing formula. It's one of the first formulas of this type. And it comes out m minus r plus j minus I, where you go from i's and j's go up to n minus r. And m and n arbitrary in this case. So this is the first of the beautiful. It's already the, we're talking about loci defined by determinant. Right? Why should the answer be a determinant? Well, nobody can answer that question. I've never heard a good answer for that question. You've probably all seen it happen in some field. Okay, so this is around 1903. So that's about the first 50 years of sketch of this thing, a couple of highlights. Now, for the next 50 years or so, the subject was pretty quiet. There were no new formulas that I know of. Well, it's one exception I'll talk about a little later. But what did happen over the next 50 years is all the machinery got started that made it possible to go beyond projective space and matrices of homogeneous polynomials. So what do you do if you're not on projective space? So you want to, what's the notion of degree? Well, in fact, and how would you multiply out things like this? What you need is some kind of a cohomology. And homology and cohomology were developed by Lefschetz and topologists. In fact, exactly to do things like this. And you also need the fact that a subvariety of like a manifold will determine a cohomology class of a manifold. And saying what's the degree of that class is asking what's the class of that cohomology class. And then in terms of what? Well, in terms of something that should be analogous to these x's and y's that come up here. And so anyhow, those things are called Chern classes. So what happened over the next 50 years is people developed cohomology, had vector bundles, and Chern classes. And at the end of about that 50 years, so when Tom asked, he had a map of vector bundles. So okay, sigma is a map of vector bundles. So map on X. Let me say a non-singular complex manifold, well, complex variety manifold. So vector bundles just means a family of vector spaces, and you have a family of maps from these vector spaces to this vector space, and you have this a locus omega r, which is sitting inside our X, which says that the rank of sigma of X is less than or equal to r. And the question is, you want to find a formula for the class of this, right? And in fact, it should be an H. Well, if you're using cohomology, m minus r, n minus r. Right? And you want to, what is it? Right? And so he had a nice paper. He proved it must be given by a polynomial in the Chern classes. And the reason was that he could pull it back from some universal case where there wasn't anything that wasn't polynomials in Chern classes. So this was a nice idea. So it had to be a polynomial. And he got together with Porteous, and Porteous managed to find Giavelli's paper and looked at it and saw that formula. And this Tom Porteous formula says exactly that it's equal to this exact same determinant, the same determinant, Giavelli's determinant. And but what's C? Well, C, I'll just write it, is C of E over C of F. So, and for those of you who know about it, this A that you're looking at then is really a map on on projective space, you have these line bundles O of any integer. And I think I said it was plus, so I should put a minus in there. This matrix A that we were looking at. The right modern way to look at that is to say it's a map of vector bundles on projective space from the direct sum of these line bundles to the direct sum of these line bundles. And the Chern class of this is exactly that numerator I wrote there. And the Chern class of this is exactly the denominator I wrote there. And so Porteous looked at that and said, obviously the formula has to be this one. And then they had to prove it. And that's the beginning of the modern story. So that's in the 1950, 60 time period. One interesting thing about this, which actually goes all the way back to Bazoo, you ask, when is it true? So I'm avoiding that question a lot. So for example, here, they had to assume that this map was extremely general. It was in general in every possible way. So not only was, I mean, everything was as smooth as it could be, everything had to meet everything else in the right. So for example, even if this locus was empty, that doesn't mean this map was good enough. So it's not even necessarily a formula for the empty locus. I'll come back on that. And so in fact, the place where I got interested in this was Kempf and Laxoff wrote an absolutely wonderful paper where they did this in algebraic geometry terms, and they proved it. So it's I'll just say it, it's true. So whenever this omega r has the codimension it's supposed to have, so equal to m minus r times m minus r. So you don't need to assume generic in any wild sense. You just need to have it the right dimension. Of course, you have to count this cycle is counted with as multiplicity. So, and they had to say what they were. So just like when you have a couple of plane curves intersecting, you count it with kind of a naive algebraic multiplicity. And they together with Kleinman gave absolutely beautiful application of this formula. The simplest case of it is you take a compact Riemann surface, you know that you can write it as a branched covering of Riemann sphere. And the question is, how many sheets do you need? And the answer, in fact, is, so this is an application, I think, so if G is the genus of it, I think, hope I get the numbers right. I think it's that. But again, try proving that by hand. So, so genus 1 and 2, it's a 2-sheeted covering, 3 and 4, it's 3-sheeted, and so on. I think that number does that. Anyhow, so how do you do this? Well, they set it up as in fact, the classical people set it up as a locus, which was locally given by a matrix. And they said, well, that matrix, by the codimension, it predicts it should be non-empty, so they said it was non-empty, but they didn't give any justification. Well, the right way, you set this up as a problem on some variety, either the Jacobian variety of the curve or a symmetric product. You find a couple of bundles, and you find a map between them, and you reduce this problem to proving that a certain locus is non-empty. And how do you prove it's non-empty? You compute the right-hand side and prove that it's not 0. And if that polynomial is not 0, then the locus is not empty. So that this polynomial not equal to 0, that implies that not empty. So this is a typical application of that's why we want to know formulas for the like this. Then, and in fact, that didn't follow from René Thom and Tom Porteous, because you don't know anything about how general these maps are. But empty or not, you certainly can say. So I remember seeing that as one of the beautiful early applications of modern thinking about intersections. Okay. Right. I'll say just a word or two about There's a generalization of this. So let's look at some small matrices, and 3 by 4 matrices. And I'll look at a permutation, but so this one is going to be 2, 5, 1, 3, 4. So this is the permutation that takes 1 to 2, and 2 to 5, and 3 to 1, and let's see, 3 to 1, 1, 3, 2, 3, and 4. So those are kind of outside our matrix. So if you like, you can expand your matrices to be bigger, like 5 by 5 matrices. There won't be any interesting conditions outside when you do this. So the idea is these have to be increasing when you're outside. I'm just trying to tie it with the old m by n matrix story. And now you look at there's a locus related to every permutation, and here's what you say that the rank of the upper left p by q is, well, the way I think of it, it's like so I'll like this one. This upper 2, 3, it's less than or equal to the number of dots that we have in that thing. Right? So so it's less than or equal to the number of, I is less than or equal to p, and w of I less than or equal to q. So these are putting kind of northwest conditions on the rank. So in fact, if you look at this example, a lot of these conditions are redundant. What it's really saying is that these have to be 0 up here. There are no dots up there. And the other one that simply says that the whole 3 by 4 matrix has rank at most 2. But you put several conditions on it. And in fact, this, unfortunately, Cayley and Salman didn't look at this. If they had, they would have discovered what we call double Schubert polynomials in the 1850s. I'm sure they could have found it. There's a corresponding locus, and one way to say that in this classical case, the degree of this is equal to a certain polynomial, which is usually written with a Gothic W, and I think the way I've written things, it's kept plus x's and minus y. And this is something called a double Schubert polynomial. And so these are special cases of them. If you take the case where the permutation has R1's going down the diagonal and then increasing outside, you'll get exactly this locus. And in fact, it's quite easy to work out lots of these, and some of them are hard and some are easy. These are what are called double Schubert. And just, as usual, names of things that Schubert did an awful lot in this story. The one thing he didn't do was anything like that. Names are always crazy. And so this actually came from a series of things after the Tom Porteous and Kent Blackstock story. So Bernstein, Gelfand, and Gelfand gave some general formulas. These are very closely related to Schubert varieties, and type A it's called. And they gave formulas for them. And then and the crucial thing is Lascaux and Kirchenpuzet wrote down exactly the right polynomials for all these loci. So these are for us the general type A degeneracy loci. I think like there's one for every permutation and any symmetric group. And I won't try to say it, it would take half an hour, but these have a whole slew of wonderful properties. So one of the properties that's crucial is they're polynomials in the variables. They don't depend on which symmetric group this is in. This is part of what this thing is. So for example, if I add a 6 to this, I get exactly the same polynomial. They're stable. And if I write this out in terms of x's and y's, at least if I don't have the minus sign there, they're all positive combinations of the x's and y's. And if I multiply 2 of these together and express it in terms of the third one, the coefficients will be polynomials in y. They all have the same sign as the theorem. Nobody knows what the formula for them is. It's a huge open question. Given any three permutations, we can write down a polynomial and nobody knows what it is. It's really quite astonishing. There's a lot of work on it and many positive results, but no general formula. Anyway, these also give, if you take these y's to be kind of equivariant characters, they give the equivariant classes of Schubert varieties and flag varieties and Gaussian. There are all kinds of formulas for localizing them. They're related by difference operators. Newton's difference operators. And there are more general determinantal formulas than Gimbelli's that I won't try to write down here. But I think everybody who looks at them agrees that just everything you could dream having in what's called type A. And type A is partly you're talking about the general linear, general matrices, and general permutations. And the question is, so this is the type A story, and the question is, what about types B, C, D? And those have to do with symplectic forms and quadratic forms. So it's not just linear algebra, but linear algebra with extra structure. And somehow I think, they're practically hardwired to think, if we know what things are in type A, if we work hard enough, surely everything should be just as nice in type B, C, and D. Anyhow, that's an axiom. And so that's, in fact, the earliest paper I saw on this is again by Salman. Probably the earliest case number. You do the same thing where A is Aij is symmetric. So we're looking at a symmetric matrix, not just the general matrix. So of course, you could say, well, apply the same old formula. But of course, this is nowhere near general enough. So even the codimension is wrong. So that formula will never be right. So you could have matrices that not completely general, but symmetric matrices, very far from that. So you would, if you take them to be coordinate functions, you would have these for I less than or equal to j. So n would be n plus 1 choose 2, I guess, minus 1. Okay. And again, you have the locus where, say, omega r is the locus where the rank is less than or equal to r. In fact, the codimension of this is n minus r plus 1 choose 2. So it's not the product of those things. But you can ask what's the degree of it. So, and right, so the first case that let's see, yeah. So of course the n minus 1 is just given by the determinant vanishing again. And so n minus 2 is a something of that defined by quite a few equations. And how do you give its degree? And Salman wrote down the answer to that. In fact, and again, there was not as much work in this case. So of course, you can do a similar thing when it's skew symmetric. I won't try to do that today, but it's very similar. And Gimbelli also gave quite general formulas for this. So I said he wrote a series of papers, and the other papers were on this symmetric and skew symmetric case. And the general setting here is, I want to emphasize this for one reason. We want to talk about homogeneous polynomials of some degrees, and I want all the minors to be homogeneous. So your first thing to write down, you would write probably xi plus xj, but then you realize something wrong. I can't even include the first case. because those were all 1, right? And 1 is an xi. Right? I mean, A11 would have to be x1 plus x1, be an even number. Right? So in fact, they realized pretty early that you have to modify this, and one way to modify it is to put in some other variable. So the only one you really need is d could be 0 or 1. That's all you officially need. But you notice you need something. You want to include not just even dimensional. Like if they all have the same degree, you don't want it to be an even degree. You want a lot even and odd. And so there was quite a bit of work trying to generalize this. So I think it's probably pretty clear to you what the setting is here. If you would have a map of vector bundles, right? And it should be a symmetric map of vector bundles. And the right context for that is you want a map from E to E dual. And it should be a symmetric map. That's one way to say this thing. But in fact, this G tells you that you have to allow an extra line bundle here. And this is the setting that quite a few people worked on this. So I think Josefiak and Pascu wrote a paper about it, and a little later, Harris and Tu wrote a paper about it. And the problem was to find good formulas. You still have this locus. So this is a symmetric map. And you want to find the formula for the locus where this rank is less than or equal to R. It should be involve the Chern classes of E and also this Chern class of L, which is going to be this Z. And yeah, there were 3 papers that Prakash and I, well, two that we wrote, and then Kazarian wrote a paper that was much better than either one of ours. And the difference is we both published ours and he didn't publish it. So you can find it on the internet, but it's a very influential paper. So what's the setting? So in fact, Joe Harris had explained this to me exactly 30 years ago, plus now. So in these types B, C, and D, well, at a point you get in a vector space with a bilinear form on it, either skew symmetric or symmetric and non-degenerate. And how do you say that in families? You say you have a vector bundle and you have a bilinear pairing, non-degenerate everywhere. But the values shouldn't be just in the scalars, they should be allowed to be in a vector bundle. And you need that for this thing here. You need to have a line bundle, not a vector. So in type C, so this would be skew symmetric, so alternating forms in type C. And in types B and D, it would be a symmetric thing. Let's forget about B and D for now. The claim is everything we say goes over to those. So the question is, you want the class of this should be polynomials, and moreover, what's the analog of this symmetric group? Well, it's known to be the group of sign permutations. So if I don't have sorry, I misspoke that. Let me be more smart. The right context for this, which is kind of surprising, is so we're given this setting, and so for a skew form, locally they all look alike. There's only one non-degenerate pairing on vector space, that's the isomorphism. But globally they can be different. And you assume that E and F are maximal isotropic. So point-wise you say subspaces, but subbundles. And isotropic means that this form vanishes identically on them. And maximal means they're n-dimensional. That's the biggest thing you can have. And the question is, the omega r that we're looking at is looking at the points where the dimension of E intersect F is greater than or equal to R. This is the fundamental locus for this. And yeah, let me just very quickly say that if I have this setting with a symmetric form, and I take, there's a standard thing you can do when I have any V. I take E, the direct sum of E, and E dual tensor L. Not really, but yeah. Oh, hold on. Well, given that setting, just given E and L, I take E and this. This has the standard symplectic form on it. So given two things, I have a vector, and think of this as a map from E to L. So I have two of those. I can evaluate this thing on one of them, and the other one on this one, and subtract them. And I get a symplectic pairing. It's kind of the standard way you write down a symplectic pairing on a vector space. Symplectic. And if I'm given a map like this, there are two isotropic subspaces. One isotropic subspace is E plus 0. That's always there. The other one is the graph of sigma. And what's surprising is that the graph of sigma is symmetric, and it's isotropic exactly for this thing, when this is skew symmetric. It's exactly switched from what you would guess, but it's very easy to check. And so the locus where this has rank at least something, actually it's the opposite one. I want the kernel of that to be at least a certain size. That's exactly the locus where these two isotropic bundles be. And it was Joe Harris that pointed out the right way to do these formulas is not to look at symmetric matrices, but to look at type C phenomena. We have two maximal isotropics and look where they meet. And one of the things that we have is a good formula for these things now. And for those who want, if you're in the general case that E and F could be filtered, so that's the analog of taking these upper northwest corners of the matrix where you look at subthings. And then for W in a thing called the Weil group, which is the set of all sign permutations of all the integers that are the identity beyond a certain point. And I think you can imagine that for any such thing, you can write down a locus that tells you how all these filtrations in this one meet all the filtrations in that one. It's like what you write down for Schubert variety. And there is such a locus. And the problem is, can you find a formula for that locus as a certain polynomial? And this is a long history. So in the so I said, we wrote several papers, and our formulas weren't the same. We had different formulas for loci, which couldn't happen in type A. There's a unique formula. Everybody getting it in any context is going to get the formula. And we were getting different formulas. And there's a reason, and that's because these bundles that come up, and they're not independent of each other. Like these E and F, they're relations among the Chern classes of these things. And it made the problem a lot more interesting. So Fulton and Kirillov systematically sat down and said, here are the properties you would like for these double polynomials, or in fact, single polynomials. And they made a list, and then they said, you can't do it. There are no polynomials that satisfy all four of these conditions. You could maybe get 3, but not 4. And at just about the same time, and they were aware of it, Billy and Hyman did give such polynomials. So, but the difference is they changed what they meant by a polynomial. The polynomial was a power series. It had some kind of infinite to it, but it had all the right properties for these things called single polynomials. Those are the ones where you don't have the second variable. And then Ikeda, and Mahalcha, and Russo found double versions of these. And again, for all types B, C, and D. And so what I want to say a little bit about in the last few minutes is I guess we were just chatting. It's more than 5 years that we started on this. So to give to give formulas. So for these, so in what, especially not entirely this, but including with the line button. So. And I mean, the reason, from my point of view, the reason, if you don't have L, you can't even do the first case that was done in 1862. You've got to be able to have a line bundle. Okay. One way to get around that is to somehow take a square root of L and take sort of half C. And in fact, classically, they did that with. Part of our point of view is by forcing yourself to say it right, it should also force you to write down the right formulas for it. And that has been pretty much the case. So the claim is that we have such. So that's BW. And so what's kind of surprising and took us quite a while to realize, and kind of anticipated by it. So they're not just polynomials with Z coefficients. So that's part of this thing of Fulton and Kirloff and Billy and Hyman. They're a ring, what we call it, boldface gamma, with variables X and Y. And this gamma is not just Z, and it's a more interesting ring, and I'll say what it is. So gamma, well, I'll start to say what it is. I take a variable Z, which is corresponding to that extra degree you get from a line bundle, and I want Chern classes, so I'll just write them as C1, C2, and so on. And then there's going to be some relations, which took us quite a while to find them. Okay. And the key thing about it is this is free, so over Z of Z on, well, some things we call Pfaffians, but they are Pfaffians. And so certain polynomials that we write down involving the C's and the Z in this thing, which are Pfaffians. So Pfaffian, this lambda is what's called a strict partition. So lambda 1, lambda 2. And so the polynomials that are written down are going to, one of the assertions is that they can be written uniquely in terms of the C lambdas and powers of Z and monomials and X's and monomials and Y. And one of the claims is that they're positive in every single one of them. So it's the positivity that they found in type A works in type C and other types. And when you multiply these together, again, the coefficients have the same kind of positivity. We know even less about what combinatorial formulas for them, but they all have the right kind of positivity. And they have essentially the whole package of 20 or so properties that the type A polynomials have, these polynomials have. So this isn't a polynomial ring, but it's just as nice in the sense that if you write things in this ring, everything has a unique expression. So you're not in this game of comparing different guesses that you make. Every polynomial here has a unique expression in terms of powers of Z, these C lambdas, and these things. So, and what are the C's? Well, for those of you who know about it, there's the C is set to, actually this was something amazingly expressed by Joe Harris, is, I'll write it in the language, modern language. So we take the Chern class of this ambient bundle V and the Chern class of E and the Chern class of F, multiply these, divide this by that, and take the ith term of that. So it's in the spirit of what Cayley was doing in the 1840s. but it's crucial that you do exactly this thing. So this is the ambient bundle, and these are the two isotropic subbundles. And one of the one way to say what are the relations among these? Well, the relations are exactly saying what are the relations among these. And it's one of the nice things about Chern classes is you can compute your heart's content, and we've computed long beyond our heart's content, and finally found the relations for these. So I'll tell you what this is in some examples. So what are the formulas for these formulas where the dimension of E intersect F is at least 1? And this one's an easy one. It's exactly C1. I think that anybody who knows about Chern classes and could figure that one out. But already the second one is a little, so the second one actually gives Salman's formula. And so it's kind of a funny looking formula if you've never seen them before. If you've seen things called Q polynomials, these expressions come up a lot. And what this is our twist of that because of the line bundle. And and I want to say et cetera. So the question is, can you see what the et cetera is? And let me write a couple more that don't quite make sense until I say some more. But for example, the formula for the next one is so that in fact is, I told you that there are these polynomials in here. But this one is what we call C 2, 1. So for the partition 2, 1. So this is one of our basic elements. And we need a lot more of these. So for example, for C3, if you know about Pfaffians, it's what do you want? Something like this. So I haven't defined all those things yet, and let me give you the next one. I think then you will see the pattern. So if you've seen Pfaffians, you've certainly seen this formula. These are the square roots of determinants and the Pfaffian of a thing. So this is our C3 to 1, and this is C4. And
what is C3?
so right, exactly. I haven't told you. I told you what C21 is. I haven't told you. So in fact, here's what CPQ is. So, and quickest way to write it is like this. So I take all increasing sequences, A less than equal to B less than equal to Q. And I take -1 to the B, and then I take the sum of two coefficients, and Z to the A, C to the P plus B minus A, and C to the Q minus B. And that, so if A is equal to 0, this expression becomes exactly the alternating sum of twice the neighboring things, which was known to Schur for Q functions. And this, with the A in it, this is our twist of that classical thing. So of course, I didn't want to start the lecture with this because the room would have been empty immediately. So in fact, I can tell you what these relations are. Now these relations are exactly saying that CPP is equal to 0. Where you take P equal Q in this one. So we were forced to this, and it took us, I don't know how long before we found it. My first proof that it was right involved Dave going into the Maple code that was computing hypergeometric functions. But now we know nice proof. Now, this ring gives us a nice description of the cohomology or the Chow ring of these Lagrangian bundles, which I found much better than any previous one because it's completely stable. If you notice but sometime there hasn't been an n around, right? I mean, it's there, hidden, but nothing we write down depends on n. And so the claim is that the cohomology of the Lagrangian are given by generators like this and relations like that, plus some relations that say that they vanish beyond that. Yeah, let me give one application which doesn't need any more formulas. So like I said, there were many papers giving formulas for this, where this is symmetric. And you have this locus. So now omega r is where the dimension of the kernel is greater than or equal to r. So it's omega n minus r in the old notation. And in fact, the claim is that it's exactly this C for r minus 1 down to 2, 1, where C now is C of E dual tensor L over C of E. So again, it turns out this is a special case of that. So there's a map from gamma to that, which takes Ci to the ith term of this. And if you apply this definition of the C's and use it to make Coffin, you get exactly the formula. And sometimes you have to work a little to prove that the formulas of Salman and the ancient special cases. So type B and D are quite similar, except you have to get away from Chern classes. So the tradition is in type B, you just divide everything by 2, and you talk about half Chern classes. That's not the right way to think. A half Chern class isn't a Chern class. You need something geometric. And there's some geometric things that are related to Chern classes by formulas involving 2s, but it's not just multiplication. But once you've got them, you can write down similar Coffins and you have similar formulas. And type D, there are some other things that are even farther from Chern classes. We call them C's and B's and D's, and type C and D. That's pretty imaginative. Yeah, we should try to do better. Okay, stop there. The B's is pretty close, yeah. But it's more different than it was in the classical case. When Z is equal to 0, you get it done classically. And there, the B's are just half. But and RB, so twice a B plus something else is equal to a C. And so it's sort of in principle determined by it. But, yeah.
What exceptional types?
Yeah, so, right, so I think only one type has been pretty well worked out, and that was by a student of mine in his thesis, and he said they then thesis. So he did type G2. And I think that's still pretty much where it stands, right?
Other types that they have to ask.
I think there's suspicion that maybe type F4 might be doable by similar methods. It was not trivial what he did in the thesis. And type E looks quite a bit harder. But it could just be one great idea. If you get 50 mathematicians together who know about exceptional groups and ask them what's the essential thing about G2, you'll get 50 different answers. Maybe unless 2 are working together very much. So it could be that one of these ideas is the thing that will make things work. So from our point of view, the kind of thing you want to do is you want to talk about families. Right? So you should not, you know, everything, your families of maps, families of bundles, and vector spaces. So you have to say what you mean by a family of things that G2 types. But what does it mean for them to degenerate and meet each other? So for G2, they did it. But one key thing here, remember I said was stability. That's probably our fundamental axiom. Anything we write down should be stable. When n goes to infinity, it doesn't change. And that doesn't make any sense in the other types. There's no, you don't have that. You could say you don't have that to worry about, but it also doesn't. It's a big help here. It kind of forces you to do things right. Because if you determine to do it this uniformly for all n at once, without explicitly involving n, it forces you to write down the right thing. So maybe that's why exceptional groups are hard. It'd be nice for somebody to do it.
Okay. More questions?